Okay, welcome everyone. Thank you for coming. People are still trickling in, but I think we should get started. It's a pleasure to have Veer Bulchandani here with us today. Veer is finishing up his PhD in Berkeley and actually will be joining us in Princeton in the fall as a fellow at the Princeton Center for Theoretical Sciences. He's a condensed matter theorist who has responded to current events. And he's going to talk to us today about digital herd immunity. Let me remind you a little bit about format. When we're all in person, I think we really enjoy being able to interrupt in proper physics style. That's a little hard by the time we get past 40 people online. So I've encouraged Vera to pause with some regularity in the talk and have a look at chat or have a look for people raising their hands, and we'll try to take questions that way. Either he'll manage it or I'll do some moderation, and we'll do whatever we can with the available time. So in the meantime, let me remind you all to mute yourselves. And without any further ado, Veer, please.
Hello, everyone, and thank you for the opportunity to speak here today. I'm going to tell you about digital herd immunity in COVID-19. I'd just like to start by thanking my collaborators. Soumya Shivam and Sanjay Mudgalia are both condensed matter theory grad students at Princeton, and Professor Shivaji Sondhi inspired us all to get working on this topic. Our group also benefited from discussions with Shoaib Chakravarti, a former Princetonian physicist and policy expert, Professor Vijay Raghavan, a principal science advisor to the government of India, and Brian Grenfell, an epidemiologist at Princeton. So how did we get started on this project? Well, our goal was to quantify the effectiveness of app-based contact tracing. And the immediate motivation was along two axes. Firstly, the fact that lockdowns are economically ruinous. The situation we all find ourselves in at the moment is not very pleasant. So we were motivated to think about whether smart approaches could get us out of this mess. Another strong motivator was India's particular challenges of scale. The simple fact that physically testing a sizable fraction of 1 billion people is clearly infeasible. And one advantage of app-based approaches is that they are, in principle, readily scalable. So this was why we got interested in the question. But when we tried to look into it further, we found that actually, based on the existing epidemiological literature, the values and the meaning of these compliance thresholds were somewhat unclear. So although mathematical epidemiologists had studied contact tracing before, there was actually a scarcity of analytical results in the COVID regime, which I'll try to explain below. So I'm now going to just introduce some basic epidemiological notions viewed through a physicist's eyes, which will hopefully help you to place the discussion in context. So first, just a reinterpretation or representation of the simple notion of herd immunity. Consider a disease such that each infected individual goes on to infect R0 individuals on average. This is a cartoon of disease transmission, and one natural question one can ask is, how many of the population need to be vaccinated to guard against further spread? Now, if a fraction V is vaccinated, a fraction 1 minus V are susceptible. So a new case infects an infected reproduction number of R0 times 1 minus V on average. If R is greater than 1, the epidemic continues to spread, because the source infection results in a geometric series, 1 plus R squared, and so on, of total infections. By contrast, if R is less than 1, this series converges, the epidemic does not spread on average, and this is precisely the notion of herd immunity, as given by the simple geometric series threshold B star. Now, for R naught is 3, this is 60%, and this is the controversial policy that was pursued initially in the UK. Now, ideally, disease spread would stop at 60% immunity, but the collateral damage, as we found, would be huge. And furthermore, the disease dynamics typically overshoot. So even if you were to aim for an endemic immunity of 60%, you might find yourself at something like 90. So this is another reason to think about alternative approaches rather than simply slowing down the catastrophic progression. So how is this related to physical concepts like phase transition? Well, to obtain this mapping, it's helpful to think about this as a branching process. So a few generations of this process are illustrated in the figure, starting from a symptomatic initial node. And you see that the branching process halts every time there's an immune node, but can continue propagating through symptomatic nodes. So in other words, there's an epidemic phase if an initial infection propagates to infinity on average, and an immune phase otherwise. And this can be mapped to a classic model in statistical physics known as site percolation, where one has a lattice and sites are occupied or not occupied with a given probability. In fact, the technical word for this epidemic model we're looking at is that it's the epidemic branching process of site percolation on an infinite Cayley tree or beta lattice with coordination number 1 plus R naught. So from this, one can construct a useful dictionary to go between epidemiology, statistical physics, and more mathematical language. Epidemic spread is equivalent to a non-zero percolation probability, is equivalent to uncertain extinction of your branching process. So when we talk about a phase diagram later on, what we really have in mind is this paradigmatic model of classical statistical physics, this site percolation. Now, of course, there are sources of stochasticity in real life. There's stochasticity in time periods, stochasticity in the degree per node, and fluctuations due to percolation itself. We'll be ignoring these effects, but even so, it turns out that this branching process, simple branching process, captures the essential features of what's going on. So the stochasticity in degree, for example, is where things like super spreaders would come in. It's possible for one node to have 20 offspring. We won't be taking that kind of thing into account. Okay, so I'm now going to introduce some stylized facts about COVID-19 that are necessary for understanding contact tracing. So there are two types of infections, it seems, symptomatic infections and asymptomatic infections. Now, the symptomatic ones are characterized by 3 important time periods. There's this incubation period lasting 5 to 6 days, a pre-symptomatic contagious period lasting 1 to 3 days, followed by a symptomatic contagious period lasting up to 14 days or more. By contrast, for asymptomatic infections, one never sees symptoms. There are only 2 relevant time periods, the latent period of, again, around 5 or 6 days, and this non-symptomatic contagious period lasting now for the duration of the infection. Now, in real life, there is some stochasticity in all of these time periods, but what we've described here is the mean. Now, the data before interventions is also consistent with a basic reproduction number averaging around 3. So we'll take that as input for our model. And the other parameter we're going to need is the fraction of infections which are asymptomatic, which we'll call theta. Now, unfortunately, by its nature, this number is very hard to estimate. It seems that it's at least around 50%. One can find more pessimistic and more optimistic estimates in the literature, but we think 50% is reasonable. So given these parameters, how does contact tracing work? Well, if all cases were symptomatic, contact tracing would actually work perfectly in principle. And this is the reason why. So suppose we have patient 0 in a given population who exhibits symptoms on day 7 of infection. One can then, assuming they show up to the health services on that day, one can identify their contact on the days prior to that, when they were in the pre-symptomatic infectious period or omega period, and test and quarantine rapidly as needed. And in fact, if you do this sufficiently effectively, you're done, because new infections take more than 4 days to become contagious, and you can catch them first. In the language of the previous slide, this omega period is smaller than the latent period, which is why this approach works. And indeed, some diseases are controllable in this way, for example, SARS and smallpox, but it appears not COVID with this simple kind of tracing alone. And there are 2 difficulties in general. Firstly, that the number of asymptomatic spreaders is non-zero and could in fact be appreciably large. And secondly, not everyone is going to be on the network. So the fraction of people phi whose contacts can be traced is never 1. And the sharp question we wanted to try to answer is whether one can still achieve epidemic control given these inefficiencies. So in the rest of the talk, it will be convenient to think of this fraction phi as the fraction of people running a contact tracing app. It's maybe worth briefly sketching how one actually detects asymptomatic spreaders. So with contact tracing, this works as follows. Suppose everyone is on the network, but patient 0 is asymptomatic. Then they're only going to be detected once they actually give rise to another symptomatic infection that's on the network. What this means is you have to go back in time to trace asymptomatic spreaders and then go forward in time to trace the infections they give rise to. So some element of recursive tracing is needed to catch asymptomatic spreading. The other way to catch asymptomatic cases is by random testing, but of course this isn't scalable. And we've converged on the view that actually the only scalable way to limit this kind of transmission is some combination of tracing and testing, which I'll get back to later. But for now, the goal is to understand simply the phase diagram of epidemic spread with these 2 tuning parameters. Beta, this asymptomatic rate, and phi, this contact tracing rate. And one can envisage a tentative phase diagram like the one shown, where there's an epidemic phase if too few people are using the app, or too many people are asymptomatic, and an immune phase if enough people are on the contact tracing network, or many of the cases are symptomatic. So I'm now going to back this up with some numerical and analytical results. And maybe now is a good place to take a break for questions.
That tracing works.
Right.
Too many people are asymptomatic. I want you to be comfortable.
I'm
now.
okay. Okay.
Sorry, was there a question?
So we do have one question in the chat, which was about whether there are other diseases that have that are asymptomatic but contagious.
I think most diseases have a small fraction of asymptomatic contagion. So this one paper, there's this classic paper in quantitative epidemiology from 2005 in PNAS. I think it's by Christoph Fraser and collaborators. And they go through several diseases with different asymptomatic rates, such as SARS and smallpox, and discuss whether contact tracing is effective given these asymptomatic rates. So there are other diseases, and people have studied the difficulties of it before. But perhaps not.
There are also things that have very long latencies, right, like HIV. So.
Yes, exactly. You could have a pre-symptomatic period that's very long. as well.
It's not asymptomatic, but the latency is long. So.
Mm-hmm.
Other questions? Okay, why don't you keep going?
Sure. Okay, so I'm just going to say a little bit about our choice of model, why we focused on a branching process type model. The goal was just to come up with the simplest possible model with the essential features of COVID spread that we were interested in, including asymptomatic transmission, pre-symptomatic transmission, and contact tracing. Now, from an epidemiology point of view, features 1 and 2 are important. They explain much of the difficulties, I think, that public health officials have faced in understanding and managing COVID spread. But these are possible to incorporate in simpler models. Now, what's not possible is this contact tracing. So to incorporate contact tracing, you need some notion of a contact network. And this rules out the simpler compartmental ODE type models that maybe you've seen in the literature. And as the simplest kind of model with a social network in place, we decided on generational branching process models because they're expressive enough to capture the features we need, but also simple enough to be somewhat tractable. And because of the way the branching process grows in time, this memoryless kind of behavior, this is valid for well-mixed populations at early times. If we wanted to obtain more realistic behavior at longer times, we need some notion of network structure and some variability in the number of nodes. So I won't discuss that in this talk. The system to have in mind is, for example, a large city when there are still relatively few infections, and so this branching process kind of model is roughly valid. So what are the parameters? Well, I'll start by defining the model with no contact tracing, and we suppose that infected individuals are either symptomatic or asymptomatic with this probability theta. We'll also assume different reproduction numbers for symptomatic and asymptomatic individuals. So a symptomatic individual is taken to infect RS people in each generation, while an asymptomatic individual infects R0. The motivation is that symptomatic individuals will tend to be isolated after showing symptoms, whereas asymptomatic individuals can infect freely. And reasonable parameter values are an RS of around 1, an R0 of 2 to 3, and a theta of 0.5. So this is the model without contact tracing, and just to give some intuition, here are a few steps of it. You can see this epidemic control will depend on an effective reproduction number, which is the mean number of offspring per node, and without tracing, the intuitive result, where you simply average according to probabilities, turns out to be exact. So this is a very simple model, captures the essence of the disease spread. Now let's introduce contact tracing. So as mentioned previously, we'll take phi to be the probability of being on the network. And there are 4 types of susceptible node that you can consider. You're either asymptomatic on the network, which we call CA, symptomatic on the network, CS, asymptomatic off the network, NA, or symptomatic off the network, NS. So there are these 4 types of nodes you're sampling your branching process from now, and the effective reproduction number is going to depend on these 4 more microscopic parameters of disease control. And the goal is to understand when R is less than 1. So how do we model contact tracing in this branching process approach? Well, let's start with an asymptomatic node on the network. Now in figure A, this goes on to infect 3 additional people in generation 1. We still can't detect the initial node because no symptoms have been observed yet. In figure B, we evolve the disease for one more generation. So this shows 2 generations, by which time the symptomatic case on the network in generation 1 has shown symptoms. So that's the node with the red exclamation mark. And when that node shows symptoms, an alert is sent out to the entire network connected component along the arrows shown. And figure C depicts simply tracing and isolation of this network connected component. Otherwise, the branching process is allowed to continue. So this is how we implement contact tracing in this model. It's worth maybe summarizing the difference between recursive and non-recursive contact tracing. So a lot of the traditional epidemiological literature focuses on non-recursive contact tracing. The reason being that in traditional manual contact tracing, you can only go back 1 or 2 steps up the transmission chain. It's too labor intensive to do anything more. Now, the problem with this is that if the rate of asymptomatic transmission is too high, contact tracing won't prevent epidemic spread. And simple mean field reasoning gives you the value of this threshold. It says that traditional manual tracing fails if the effective reproduction number for asymptomatic cases is greater than 1. So if you can have a purely asymptomatic epidemic, then understandably, contact tracing with a few steps is ineffective. And COVID-19 appears to be precisely in this danger zone, when it is possible for an epidemic to be sustained in the purely asymptomatic population. So given this issue, our hope was that recursive contact tracing, which goes arbitrarily far up the transmission chain, might get around this apparent barrier. And indeed, this is the case. So I will now argue why. Of course, the issue is it's only practical to realize with smartphone apps. You can't have manual teams going arbitrarily far up the chain, but the good thing about apps is they're scalable. So this might be one route to containing asymptomatic transmission. So this plot shows our numerical simulation. We took R0 equals 3 and varied the rate of symptomatic transmission to model varying effectiveness of, say, healthcare interventions. We also varied these parameters theta and phi. The black squares show epidemic control. The white squares show epidemic spread. And you can see that regardless of the rate of asymptomatic spreading, actually epidemic control is achievable for a high enough rate of app take-up. So this is the question we were trying to answer. Going into the study, it wasn't clear to us that the required rate would be less than 100%. In fact, it is, though it can be rather high depending on the rate of asymptomatic spreading. So the details on these plots are analytical predictions. Before I give actual quantitative estimates, I'll just go into the statistical physics of how we got these analytical predictions. I'll also talk a little bit about the universal properties of this phase transition, viewed as a percolation type transition. So let me start by considering the line theta equals 0 on the bottom of these plots. This is when everyone is symptomatic. So there are only 2 types of node, either you're on the network or off the network. And by adapting a standard technique from percolation theory, namely determining the probability of formation of an infinite cluster, you can actually find the exact critical point for epidemic control. And so this is what equations 1 and 2 show. You're self-consistently obtaining the probability of a node spreading to infinity. And from there, you can obtain the value of the critical point. You can push this type of calculation further to obtain the exact cluster size distribution. So I believe this method was introduced by Fisher and Essen in the 60s. By adapting what they did slightly, you can get the full probability generating functions for the cluster sizes in an implicit way. And now these are actually quite hard to solve directly, but they can give you the mean cluster size without much difficulty. So from here, you can go on to deduce critical exponents. And what you find is that even though this transition is more complicated than mean field site percolation, it lies in the same universality class, which makes sense because university classes are somewhat robust. Now, where things get interesting is on a different line in the phase diagram. So this is along the right-hand side, when everyone is now on the tracing network. And to understand why this is unusual, it's helpful to consider increasing the contact tracing depth. So this is what the figure shows. You're steadily increasing the depth of this recursive contact tracing. And what you find is that the critical point actually flows with the tracing depth. And it flows in such a way that even though you see mean field behavior for any finite tracing depth, the limiting behavior is actually a discontinuous phase transition. And one can show this explicitly by writing down the branching process in full, finding the probability generating function, and from there getting the extinction probability. You find that the order parameter for this transition, which is the probability of formation of an infinite cluster, actually shows discontinuous behavior at this critical point. So to summarize, each critical line interpolates between a mean field percolation transition and a discontinuous transition. The two endpoints we can really solve exactly. It doesn't seem possible to get the critical line in the middle enclosed form, but it does seem to show mean field exponents. These dashed lines are exact results from 10-step contact tracing, and I'll just briefly summarize how we got them. So this was actually quite hard work, but by adapting the methods in the previous slides, you can find a recursive way to describe n-step contact tracing, obtain the exact critical point in terms of these rather involved recursion relations. So this is some complicated polynomial in theta and phi. But the series appears to converge rather quickly. For even 10-step contact tracing, it seems to be converged. And again, you find this mean field type behavior where the mean cluster size is determined by the leading behavior of some analytic function. There's no closed form, but it seems to be mean field-like, except that the gradient diverges as everyone is on the network. So you can understand this behavior as the fact that on the beta lattice, mean field universality is very robust. It wants to break down as you increase the tracing depth, and the only way it can do that is by through a diverging gradient, even though the exponent stays the same. So I won't spend any more time on that. Are there any questions on this part of the talk?
I have a question.
Yeah.
When you define R naught, like R naught equal to 2, in your branching process, each person meets 2 other people and infects them. But the way I think about R naught is that each person meets 100 people and infects each one of them with a probability of 2%. So in fact, you have
that's certainly a more microscopic way to think about it, but that we obtained roughly the same. So other people did this kind of modeling, and we obtain roughly the same quantitative threshold. So I agree there are more detailed ways to treat R0, but for capturing the essential sensitivity of this model to things like theta and phi, I think this approximation is fine.
But it looks to me like it would be much more difficult now to trace back the source of the infection if you met 100 people before and one of them was infected.
Well, if it's a proximity-based scheme, do you mean difficulty practically or difficulty analytically?
No, practically. I mean, in your case, if you go back up the tree, you know who was, even if it was asymptotic, you know who was the source of the infection. But now, I was connected to 100 people, and I know that, and only few of them were on the network. I mean, it's more a probabilistic now issue. Who was the source of the infection?
That's true, and I think what this reflects is the method is only scalable really if you combine it with testing. Because otherwise, if you have 100 people going back and they generate another 100, of course, that's quite infeasible. So I think one would need to test all 100 of those people to make this approach feasible, or do that in some intelligent, random way. But 100 is a rather large number. I will say the average number of contacts seems to be more like 10 or 20. Sorry, there was another question? Or?
So I actually have one question. I mean, I realize that you try the simple case first, but I guess what I'm worried about is the assumption that people sort of belong to the are traceable or not traceable at random. And I guess I'm imagining that there are scenarios in which the people I'm like, if for example I'm not on the network, it's possible that I preferentially have contact with people who are also not on the network.
Oh, absolutely. That's the kind of correlation we've thrown out.
I guess the question is there a direction of that correlation in which you could really have? I mean, obviously it makes a quantitative difference, but I guess the real issue is whether in that direction there's another transition, in some direction of that flavor, there's another transition where you would really lose the ability to control the epidemic.
That's interesting, and actually not something we've really thought about. I would assume so, because if you're preferentially transmitting to people off the network, then suddenly it becomes much easier to have an epidemic off the network, and I would assume that critical line shifts. But haven't thought about it in general.
So I think this sort of thing is best designed for large, well-mixed populations such as cities, where the problem of contact tracing in many cases is most acute.
Good.
Agreed.
Okay, should we go on?
Okay, so that was most of the purely scientific part of the talk. Now just some practical details. So for R0 equals 2, we found a required uptake up of between 50 and 75%, depending on whether you're optimistic or realistic about asymptomatic transmission. And if R0 equals 3, this range jumps from 75 to 95%. Now, this is consistent with more detailed modeling, which, for example, has this time dependence of infectivity taken into account. So one figure which got a lot of press coverage in the UK was the 60% threshold. Now that's since been revised upwards to 80%, and we think the reason why is that these authors, like us, became more pessimistic about asymptomatic transmission. So just to say that this very simple branching process model gives quantitative agreements in quantitative predictions in agreement with the more sophisticated modeling. And these high thresholds suggest that tracing should probably be used as an effective intervention in combination with others. It seems somewhat unrealistic in today's climate about issues like privacy to expect such a high rate of app take-up. On the other hand, it is a useful intervention and could be used to bring down this effective herd immunity threshold, in the sense that if the goal of the game is just to decrease R, several measures might be effective, and this is one of them. Our original motivation was India. It's worth asking whether this would be practical there. And one immediately runs into the problem that smartphone ownership is only 40%. So somehow you have to make up the difference. Well, since actually 90% own some kind of phone, cell tower triangulation is something that could work here, where you abandon the idea of identifying, say, all 20 contacts explicitly. Instead, if someone infected is detected in a neighborhood, you alert the entire neighborhood using this coarse-grained cell phone type data. Now, the most glaring issue here is, of course, privacy concerns. We don't have anything specific to say on this, other than that many people are working on it, and open sourcing the code should be a minimal requirement. It would certainly be one way to ensure that people are happy with downloading an app. But this may be the biggest obstacle to adoption in the West. So the other thing I wanted to discuss was the testing rate, since tracing is closely related to testing. Because for tracing to be really effective, it needs to be combined with some degree of testing capacity. And so we decided to look into the question of how many tests were needed. And this was something that was in the news quite a bit a few weeks ago. In particular, the estimates vary pretty wildly depending on what you're trying to achieve. So for example, for random testing, economist Paul Romer suggested that 10% of the population need to be tested. In the US, that's around 30 million tests per day to manage spread, which seems clearly infeasible given present capacity. On the other hand, if you just want to monitor how the epidemic is spreading, physicist Marcus Mueller and collaborators showed that 15,000 per day is enough for a statistically significant handle on how the epidemic is growing. So their results were for a small homogeneous country. Scaling this up to the US, around 150,000 tests seems like a reasonable figure. The problem with this is you're not managing the spread at all. You're simply watching it. Now, perhaps the most realistic
Sorry, Vera, we've lost you for a moment there.
At the Harvard Global Health Institute, arguing for 500,000 tests per day. So here the idea was that you had efficient tracing in place, and in order to make that work, you would need to run about 500,000 tests. Now, the problem with this study is it didn't really account for high rates of asymptomatic transmission, nor the testing procedures required to actually catch asymptomatic cases. So we decided to redo their analysis with our branching process intuition. So following them, let's suppose that there are 60,000 new cases on the day that lockdowns are lifted, and around 10 contacts per case that we record. Assume 50% show symptoms. And actually, we found that what happens next depends on R naught. So if the post-lockdown R naught is less than 2, you can isolate all the symptomatic cases and their contacts, and then you're done. Essentially, because your effective R naught is now just due to asymptomatic cases, is R naught times theta, which is less than 1. And this requires 300,000 tests per day, which is roughly in line with their original estimate. However, if the post-lockdown R naught is larger, as it would be in the absence of intervention, you need to trace backwards to capture asymptomatic transmission. So the figure shows one example from our branching process picture. And the point is that to capture the initial asymptomatic spreader, shown in figure A, you actually have to go backwards along the tracing network, and then to capture the asymptomatic spreaders they gave rise to, you have to go forwards again. So in total, there are many more tests than the simple estimate of the number of contacts. In the figure shown, I think it's 5 N tests, or around 50 tests are required. And what this gives you is a much higher testing rate, so around 1.5 million. But this is still a lot lower than the naive thing of randomly testing your population and testing 30 million people per day. So that's all I wanted to say, and thank you for listening. I think we have time for several questions.
So the first thing is there was a moment where the audio cut out. So maybe if you could go back a slide. Yeah, go back a slide. Maybe one more. Right. So the next slide is a revision of the argument made by the Harvard Global Health people. But could you repeat their argument? Because I think we missed that.
Ah, I see. Okay. So they were trying to, they had two arguments, which both gave the same number of 500,000. The first was that the WHO has issued a certain amount of guidance on what percentage of tests ought to be positive. And so their first estimate was saying the positivity rate in the US is much too high at the moment. If we want to bring it down, we need to be at around 500,000 tests per day. Their second argument was that if you trace around all of the contacts of your new symptomatic cases per day, this is 500,000 tests. So that's maybe the simplest way to think about the number. It's just it's tracing the contacts of all your new cases. So how we refined the argument was both having a larger fraction of asymptomatic transmission and accounting for these extra tests that you have when there's asymptomatic transmission. And we found a much larger range depending on these parameters of disease spread. So 300,000 in the best case and 1.5 million in the worst case, but still roughly the same order of magnitude.
Good. Okay, other questions? Catherine.
Well, very cool talk. I just had a question. At the beginning, you mentioned that you didn't take into consideration super spreaders, so parts of the node, they reach lots of people. if you were to actually include that in your model, can you treat that just as like a perturbation that doesn't really change much, or does it completely change the picture and really push the phase diagram picture out?
Okay, so what we've simulated so far is just some minor stochasticity, so not super spreaders, but if that R naught is varying, we found that doesn't really change the phase diagram. On the other hand, I would expect if there's significant clustering, this would change the phase diagram. We ourselves haven't looked into this, but I will mention there's a paper in the 2000s by Eames and Keeling, which exactly studies the effect of network clustering on the effectiveness of contact tracing. And I think they find if the network's clustered in the right way, it makes contact tracing much more effective. If it's clustered in different ways, it makes it much less effective. But I don't know if one can say anything that's generally valid there. But it's a good question and one that comes up quite a bit.
Can I make one comment? I think at this point, maybe, the aim of policy currently around the world is to stop us all in this metastable equilibrium, right? You stop the cases now, you don't have herd immunity, and nevertheless, somewhere on the planet, the virus survives, periodically enters your population and starts a new, cascade. So what this is technology for, keeping that in check, right? So things like super spreading events where, 100 people are in a hall, singing their hearts out and, that sort of stuff, that will have to be dealt with by hand. That's not a problem of contact tracing. It's that you really don't want that happening. So I think you should, the sort of immunization perspective, I think is sort of useful, which is to say that once you've mostly succeeded, and this is how it's being used, in China, in South Korea, it's that with these phones, the speed at which you can contact trace, and then the fact that in principle you can put a threshold on it, which is Igal was asking, do you need to talk to all 100 people? But that's one of the advantages, which is to say that thanks to your phone, you know if you were within 6 feet of somebody for more than 10 minutes, right? As opposed to just passing somebody at some distance, and your phone can be used to trigger on those. So it both helps with memory, it helps with triggering. And of course, depending on how willing you are to give up on certain kinds of privacy protections. In principle, the sky is the limit, because between your phone and the cell towers, there's generally an extremely intimate relationship. They talk often without telling you, and based on that information, all sorts of things can in principle be reconstructed, which you presumably don't want to do unless it's really sort of desperate. But if you build in privacy tools, then you can maybe mine a lot of this information without actually sacrificing any of it. So I think in terms of where we stand in the intended exercise, I should maybe add one more thing. With regard to the US, it's actually pretty unclear. We have still a fairly large number of fresh infections per day. Epidemiologists will tell you that the actual number of infections is even larger, because we're maybe detecting as few as 20%. So if that's true, the actual number of fresh infections per day across the country, if that's true, is actually quite large. And then we're not really in this regime of worrying about one new case, but rather a large number of existing ones. But even here, if you want to go around testing and tracing, New York City is now hiring a whole army of contact tracers. You're still vastly better off having such a digital system to automate and speed up the process of finding people, identifying them, testing them, quarantining them. Okay, so I think it's one of these cases where if you keep in mind the goal, I think this technology is really essential to be able to pull that off.
Bob, you had your hand up.
Yeah, I was just wondering, like in Hong Kong, I'm familiar with Hong Kong, they've only had 1,000 cases and 4 deaths. And so while you paint, I think, a really grim picture, the question is, what has Hong Kong done to get around this? It's hard to argue with your mathematics, of course, but somehow they seem to have gotten past that. So the question is, what can we learn from places that have been successful, like Hong Kong, in the United States? Is there any lessons to be learned at all? Thank you.
So, you want me to take it, or you want to take it?
Please take it. I think you're more familiar probably with what they did.
So Bob, Hong Kong I'm not so familiar with, but Taiwan, which has been similarly successful, I am. And so of course they were extremely early to get started, so they were always in the limit of dealing with dilute incoming infections. Right? They tested airports, as we discussed the other day. You get off the airplane and you get tested. So in fact, what's going on is testing, contact tracing. But when you have very few people, and you can do this all by hand in an old-fashioned way, you sit the person down, you interview them, you follow up their contacts, you have people make phone calls. Then of course you can do it. But when you have to do, now we're past that limit, right? Because that possibility we had back in January. But supposing we had simply shut down all flights, or at least I started to really screen at the airports in a very rigorous way, maybe we would have had some luck. But of course, the asymptomatic problem also makes it worse, which means to say that the usual triggers of fever and so on would not have prevented you from having people come in who in fact were carrying the virus. So I think it's really, at this point, absent treatment, I mean, your only real game is you find each cluster, you isolate people, and it's a question of whether you did it early, and is how I would answer that. There's another question on the chat, which is if the number of cases is much larger, wouldn't it make the virus less morbid? Well, so this is being discussed, which is one of the ways people estimate that you have a larger number of cases is actually by assuming that there's a 1% mortality or something like that, for the cases that you actually have. So the so-called case fatality ratio is bigger than 1%, which is the number of deaths that you get for the number of cases that you have identified. And that's what leads you to think that there's this dark matter out there of cases that you're not finding, in order that the infection fatality ratio be actually closer to 1%. Now, additionally, people are arguing a bit about whether that number is 1% or it's 0.8% or 0.5%. And every once in a while, somebody says it's 0.1%. That's this story of serology tests and so on. It seems, and it's also very much age resolved. Obviously, mortality is much higher for older people. So there's a composition effect, which is to say, if you're an aircraft carrier and in a few of those incidents with young people, then of course the actual fatality ratio is indeed closer to 0.1%. So at this point, the fact that they're missing cases in the US is actually consistent with the assumed kind of 1% headline number for the IFR of the disease, which is about 10 times which you have for the ordinary flu.
We have one other question from the chat, which is if you'd be willing to talk a little bit about R0 or R0. Are there limitations in finding an exact number? Does it vary over time as people are more careful about their behavior, washing their hands, and so on? And what do we reasonably expect after a lockdown is lifted?
Right. No, that's absolutely right. R0 is not a fundamental constant of nature. Fundamental constant of nature is something closer to if you stand 6 feet away from somebody and give them a 1-hour lecture on COVID, what are the odds that they will get infected? And if you cut down on these seminars in person, then R0 goes down. So that's absolutely right. So these numbers that people throw around, right, have to do with the early days and how infections grew. In fact, in the case of Wuhan, there's some work from Los Alamos suggesting that their initial R0 was closer to 5 and 6, rather even 2. But in many other cases, people have done fits to 3, or I think the Imperial College team, which got everybody's attention and got the world shut down, I think took 2.4, 2.5, something like that. So absolutely. I mean, as of today, under lockdown conditions in most states, the number seems to be a little less than 1. Cases are declining. And so when you get back to regular life, the assumption is that the number will creep up. So one of the things is if you can test, trace, remove people who are infectious, you can have the, if I can use physics language, the lattice scale R naught creep above 1. On the other hand, keep the effective R naught, below 1, which is what you want, so that the total number of cases will sort of, keep declining. I mean, look, again, there's also interesting uses of this kind of technology in a different way. You could imagine using it to ration your problematic proximity interactions, right? So, for example, in the case of an institution like Princeton, I mean, again, these are all things to think about. The trade-offs currently are between sitting at home, and being sort of locked up versus operating under conditions where there are some restrictions on privacy. On the other hand, you're allowed to move around more. So to come back to it, you could imagine a setting in Princeton where, you're carrying this app around and it warns you, right, that you've exceeded this product of proximity and exposure, right, in order that your effective R naught should not creep above, 3 or 2 or some such number. So it warns you at 4 o'clock, look, this is enough. I think time to go home and read a good book. So you could imagine controlling it. Anyway, that's maybe, are there other questions?
About the phase boundary calculation actually isn't in the present draft, but we're planning to update it.
Yeah, I didn't think so. Yeah. Thank you.
Okay.
Yeah. So that's
You're planning to update it? Did you say?
Yes. It's work from the last few weeks, so hasn't made it into the archive yet.
Right. Thank you. Okay.
I would say also in New York, so something else is there's probably already natural immunity at the 20% level because of the last round. And so, of course, if people knew who they are and everybody else then decided to carry a phone, you could imagine that that would give you you wouldn't have to go as far. So if the bare R naught is not 3, but is 2, and then some number are immune, you can get to an effective herd immunity at much lower levels of smartphone coverage. So the pessimistic case doesn't have to be true if you've got various other things going for you, such as a lower natural R naught.
Good. Are there more questions? Okay, if not, let's thank Veer again. And let me remind you all that we have another seminar next week in our oscillation from theory to experiment. We'll be hearing from Andy Leifer talking about local efforts to build useful things for the epidemic, to respond to the epidemic. And let's thank Veer again. So thanks a lot. And hopefully we will see you in the fall.
See you then.
Thanks a lot, everyone.